Hi everybody. In today's lecture we're going to finish off our discussion of branching processes. We're going to look at one last theorem, the criticality theorem, that relates mu to the probability of extinction. And then we're going to try out our knowledge on a little example problem, a sort of a contrived one. After that, we're going to spend just a little bit of time introducing Markov processes. We'll just make a couple of definitions just to sort of get some thoughts going about what Markov processes are. All right, let's get started. All right, so we're almost done with our tour of branching processes, or our specific example of them, Galton-Watson processes. We're going to finish today looking at those by first looking at a theorem and then testing it out on something, and testing some of the other things we've seen as well. So the theorem, it's a named theorem. It's called the criticality theorem. And it's about extinction. And so it basically relates the expectation value of the offspring distribution, or of z, or x1, to e. So we're relating mu and e, basically. And so here's what the theorem says. It has three parts. And so it says part one, if mu is less than 1, then the extinction probability is 1. Right? And so this is called subcritical. And the second part says that if mu is equal to 1, then the extinction probability is also 1. So everybody's going extinct. This is called critical. We saw this name before, I think. And the third part, I think this is the one we didn't name before, but we probably should have. It's if mu is greater than 1, that's called supercritical. Then we can conclude that the extinction probability is less than 1. And these things sort of make sense, right? If the expected number of offsprings is bigger than 1, it seems plausible that you might not go extinct. If it's smaller than 1, it seems plausible that you would, and so on. I don't know. It seems plausible, this thing. But let's go ahead and work out a proof. Okay, so we're going to start off by just looking at the definition of mu. So recall that the first derivative of g evaluated at 1 is equal to mu. Right, so that's just the definition. And we're going to require the following. If the following is true, that branching is possible. That there exists some n greater than or equal to 2, such that p sub n is greater than 0. Right, so there is some probability of having branching. Well, here p sub n is the probability. So this is the probability that z is equal to n. That's what that means there. Okay, and so then we can remind ourselves of what the probability generating function for z will look like, right? So it looks like this. The definition, you can write it out like this, right? So we'll just express the sum, right? P0, probability of z is equal to 0, plus s times the probability that z is equal to 1, plus s squared times the probability that z is equal to 2, and so on, right? So it just keeps on going like this. Dot, dot, dot. And each of those p's is positive or 0 or higher, right? And so this thing, so for S and S, okay, so it's a little bit of a funny expression. Like you can always get in trouble for different values of S. If you put those into probability generating functions, you might get a series that explode. But so let's say, so on this interval, S in the interval 0 to 1, we can make the following observation about G and its derivatives, really. So G prime and so on and higher, these guys are all greater than or equal to 0 on that interval, and they're increasing functions. With S. I guess you can see that because each derivative is always positive. So if G prime is always positive, you're always increasing, or at least you're never decreasing. That's probably, I should have said it that way before. So I should say never decreases. How do I want to write this? Let's just get rid of this. And each never decreases with increasing S. All right, so they're sort of increasing functions of S in a little more complicated. They can be flat if you want, because equal to 0 is one of the things there. And so what are the possible solutions here for mu? So possible types of mu. Possible values of mu. Let's see what these are. So there's basically 3 types, right? Bigger than 1, equal to 1, or smaller than 1, right? So these are, where did I write? These are the conditions, 1, 2, and 3 over here, right? And we're going to kind of do a sort of a proof by picture here, right? So this is sort of a proof by picture, right? So let's make a plot of, can I make that straight? There we go. On the vertical axis, we'll make this G of S. And then the horizontal axis will be S. Right? And so let's say over here is 1. And I guess I should make this square. That looks pretty close to square. To fix this. Can I erase that? There we go. Ugly. There was a better way to do this. Why didn't I do the better way? Anyways, there we go. Okay, so this is the plot I want to look at. And on this plot, I'm going to line this up like that. I'm going to draw the G equals S line. So we'll put that in red. And that line, goes up like this. So finally, the graph paper is useful. Is it even? There we go. So that's the G equals S line. So this thing has slope of 1. Right? And remember, so the derivative is always, and of course here, so I want to remind you that mu is G prime. Oh, I've still got it on that funny eraser. Mu is G prime evaluated at 1. So it's the slope when G reaches 1. Right? So let's think of the different types of values you can have. So if you were over here and you had a slope that was, let's say case 1 and 2. So let's go back over here. Case 1 and 2 is where the slope is either smaller than 1 or equal to 1, right? And as you go back to the left, as you go to lower and lower s values, the slope has to get smaller, right? So if you leave from here with a slope of at most 1, something like this, and everywhere you go, the slope has to get smaller as you go further and further, right? You end up somewhere over here. That's just an example. You hit the line over there. And so this is case 1 and 2. They look like this. If you start off with a slope bigger than 1, then you can cross this. So the key thing to understand here is that this blue line here, it never hits the red line again. So the smallest solution in this interval for G equaling S, this is E, is going to be 1, right? Because it's never going to cross that red line again, because it leaves with a slope at most 1, and then that slope decreases all the time. So there's no way to like come back down like this, right? Because to do that, you'd have to have a slope bigger than 1. But now suppose you did leave headed towards the left with a slope bigger than 1, right? So something, I don't know, something like this. Oops, I didn't want to make that like that. Something kind of like this. So that thing has a slope that's greater than 1, and as we go to the left, it has to have its slope decrease as you go. And it has to stay in this interval 0 to 1. And so it's going to cross at some point. And so this guy's case 3. And this guy has a solution somewhere over here. Right? So 1 and 2, so we conclude from this that for 1 and 2, E is equal to 1. E equals 1 is the only solution in the interval of 0 to 1. And so it is the solution. So in other words, E equals 1. And that was what we were going for case 1 and 2. For case 3, so it is kind of a proof by picture. You could probably try to make it better. So for this guy, there is another solution, right? So there exists some kind of solution. How do I want to write this? There exists a solution S in this interval, 0 up to and not including 1, with S equals G of S, right? And therefore, E is less than 1. All right, that's our proof. All right, so we've now had a sort of a foolish tour of Galton and Watson processes, which are our example of branching processes. And we're going to finish the chapter or the topic by looking at a little example. And we're going to look at an example that's kind of in the spirit of Galton and Watson, for better or for worse. And so I don't know if you remember, but the idea, I think, that was driving them, as I understand it, again, I'm not a historian, is that they were interested in whether or not certain surnames would become extinct. And so we're going to look at, so for them, the offsprings that they were interested in were male heirs, because let's say you had some population of Draskos, and there was like 100 of them or so, and each one had some offspring, and then the male heir would carry on the line, the name Drasko, if that's how you were doing your naming. It doesn't really fit with modern practices, but it does have a direct application to something less unsavory and more practical, which is genetics. As I understand it, there are certain genes or genetic traits or something along those lines that I don't know the right words for, that only follow and always follow down the male line. And so you can take this technology and apply it to that and maybe do some useful genetic calculations. Again, we're not going to be spending our time on these applications, but that's a more savory application than finding out whether or not some important surname goes extinct or not. But okay, so the idea that we're going to try here is we're going to invent a sort of a funny scenario. All right, so this is going to be a Galton-Watson process, and it's going to start with a population of 1. So x0 is equal to 1. And we're going to suppose that each offspring, each member of the population is required to have 3 children or 3 offspring of their own that may or may, or sorry, I shouldn't say offspring necessarily, 3 children that may or may not qualify as offspring. They do qualify if they're, say, male, and they don't if they're, say, female, or vice versa, whichever you want. And so we're going to say the following. So we're going to say that Z is binomially distributed with n equals 3 and p is a half. So we'll suppose that there's equal probability that any individual child is with or without the trait that we're interested in. So in other words, you could write Z as U1 plus U2 plus U3, where each of these UI are Bernoulli trials with probability of success 1/2. Right? So, in other words, each of these UIs is equal to 1 with probability, we'll say P is equal to 1/2, and 0 with probability Q also equal to 1/2. All right, and so it's 1 if the offspring or the child carries the trait. So this is child has the trait. And it's 0 if the child does not have the trait. Okay? And that's the idea. So in a way, this is sort of like it's a funny kind of, it's almost like a 3-child policy. I was thinking of the 1-child policy in China, but it's not quite like that because it's not like a n equals 3 version of that 1-child policy, because in this case, every member of the population must have 3 children, not can have at most 3, must have 3. And then each one may or may not carry the trait. And so it's a little bit different from that. Anyways. Okay, so that's the idea here. And the question that we want to answer is, so our goal for this example, or the question, is find the probability of extinction. Right? So will it be the case that this population or this trait goes away over time? If you start off with 1, every member of the population must have 3 children. The children have a 50% chance of carrying the trait. Yeah, and so that's the idea. That's the question. And you can immediately apply, so you can check, so right away, check the theorem, the criticality theorem. The one that we just proved. And for that one, what did we have? The rule was that if mu, it's somewhere up here. Here we go. I didn't really write let's go back to the top. It's easier to see it there. if mu is less than or equal to 1, then the population will go extinct. And if it's bigger than 1, then it has a probability of not going extinct. So E is less than 1. And so here, what is mu for a binomial distribution, right? So it's n times p, if you don't remember. So this is 3. You can check this in various different ways. So that's 3/2, so that's bigger than 1. And so this tells us that E is less than 1, right? So first of all, we can conclude straight away that the population is not going to go extinct for sure eventually. It doesn't have a probability of 1 of going extinct, but eventually. And so we have that already. But we want to actually find the value of E itself, right? And so here's how we do it. So in case you have forgotten, we worked out last time, and we used already. So we want to use the following. E is the smallest solution to G of S equals S in the interval 0 to 1, right? And so we're going to find out what G is, and then we'll just find E by setting G of S equal to S, right? And so this is pretty simple to do. So for a Bernoulli trial, so G for each of the U's, we can actually just write this out. Even if you've forgotten it, this is the easiest one to rebuild because there's only 2 possible values for the U's. And G is equal to Q plus P times S, right? So that's the probability generating function for a Bernoulli variable. And for a binomial variable, which is made out of these, if there's n of them, you can use this rule. I'm sure you've done this before, and I think we might have done it, but maybe not for this particular example. No, we did it in a tutorial. We found the probability generating function for binomials in multiple different ways. I think it was your first tutorial. It's going to be that if we have n trials, in this case we have 3, then this thing is Q plus PS to the n. Like that, right? And so here, what do we have? We have P and Q are both 1/2, and n is equal to 3. All right, so we want solutions. So we want to solve the following, right? So we want to have G of S, which is, so that's, what is that? 1/2 plus 1/2 times S cubed equal to S, right? In other words, we want to have, what do we have here? 8S is equal to 1 plus S cubed. Right. And so this becomes, you can see right away, oh man, it's going to be a cubic. So I'm going to have to find the roots to a cubic, and that's always a little bit messy. But we can have a bit of a cheat because, notice, so this is in principle a little bit messy algebraically, but notice you can help yourself out. S equals 1 is a solution. Right, so if you go back up here, just look there. If Q and P are both 1/2, then if you put S equals 1, you get G of 1 is equal to 1/2 plus 1/2, which is 1 to the nth power, so that's 1. And so S equals 1 is a solution in this case. And therefore, we can write this as the following. So we can write 0 is equal to s minus 1 multiplying some stuff. And if you go through the algebraic adventure to find it, what is that stuff? You get the following: s squared plus 4s minus 1. Right? So I'll leave that adventure to you. But so this is how this thing looks. And now you're only faced with finding the roots of a quadratic. And that's relatively easy. So we have the solutions. So we have solutions. We have s equals 1 is a solution, as I just said. And we also have s is equal to, and so we break out our old memory from childhood, and it's minus 4 plus or minus the square root of 16 plus 4 all divided by 2, right? But remember, we want the solutions to be on the interval, in the interval 0 to 1, and so for s in this interval, we only have these solutions. S equals 1, and s is equal to, so what is this? 16 plus 4 is 20, divided by 4 is 5. So we've got square root of 5 minus 2. Okay? And that number is smaller than 1. It's about 24%. Right? And so then we conclude E is about equal to 24%. Right? So there's about a 1 in 4 chance that this trait would go away eventually. Okay, so we'll now move on to the next main topic for the class. And so that's sort of our 5th chapter or so. And so this is Markov Processes. Right? So Markov Processes. So let's move this down to a new page. It's a big thing. And today we won't do much. We won't do much with this other than just kind of define them and get you prepared, because the next lecture won't be out for about a week. So Markov Processes, we are going to look at 2 different examples. So we will study 2 kinds. With branching processes, we only looked at Galton-Watson processes. And with random walks, we looked mostly at Gambler's Ruin, but we looked at the unrestricted random walk as well. And so these are the 2 kinds of Markov processes that we're going to look at. We're going to look at Poisson processes, or Poisson process. And we're going to look at something called the birth and death process. Birth-death process. All right, so those are the 2 that we're going to spend all of our time on. After this, we'll have 2 more subjects that we're going to see, 2 more kind of chapters, queuing systems and hidden Markov models. But we'll get to those after we finish this topic. Okay, so what are Markov processes? What's the difference between this and a Markov chain? All right, so here's what's going on. So the major change is very simple. For a Markov chain, you have discrete time. And for a Markov process, you have continuous time. Right, so this is chain, and this is process. You, I think, won't have to look very far before you find people who maybe use a slightly different terminology for this. They might just say Markov chains can be either discrete time or continuous time. and they won't really distinguish using the word process. And so you should just be aware of that. Not everybody uses the word process in this way, right? But so in any case, that's what we're doing. And so for us, the chain looked like this. So we had x sub t and t or n we use sometimes. This was 0, 1, 2, and so on. So that was the chain. And for a Markov process, so this is what we're going to use now, we're going to say x of t, and t is greater than 0, greater than or equal to 0. It's a real number here, right? So that's the change that we're going to look at, and it has a variety of ramifications. And so one thing, for example, the distribution vector, so u at 0 is one thing that we're going to pay attention to, and the transition, the n-step transition probability matrix. So these guys, they're essentially the same. However, what we pay attention to is when did the transitions occur. In other words, well, so let's just look at these details as they come. Oh, and so the main thing that is exactly the same, so not changed, is that the state space is still discrete. Right, so we're still going to have a discrete state space. Okay, so let's just introduce the definition, the formal definition. So let's make it in red. So the definition of Markov process. So we'll say that a Markov process and then we'll write it out, x of t such that t is greater than or equal to 0. So that's the thing that we call the process, is a continuous time Markov chain so there's still some sort of memoryless process property. It still has a discrete state space. Discrete state space. And we'll write out the memoryless property here, the new version of it. Right, and so it's going to be long, so we'll probably have to break this equation across 2 lines. But so we'll say it looks like this. The probability that x of t is equal to I sub t, given that x of u is equal to I sub u for u that's smaller than, or it's in some interval 0 to s. Right, so that's the probability that we want to be interested in. The sort of generalization of the memoryless aspect of this is, remember before we would sort of erase all of the times earlier than the nearest one. And so we're going to do that again. So it turns out that you don't actually need to pay any attention to x of u except at the nearest you can get to t. And so this is going to be equal to the probability that x of t is equal to I sub t, given that x of s is equal to some I sub s. Yeah. And so then we have to make sure that things don't cross over here. So we'll say that for all, how do we write this? T is bigger than S. And T and S are real. All right. So that's the definition of a Markov process. All right, now we're going to define what homogeneous means. For Markov processes, it's a little bit different. And then we'll just give a few little examples and just kind of talk about them. Okay, so one definition. So we say that a Markov process is homogeneous. A Markov process is homogeneous if the following is true. So we'll say that the probability that x of t equals I sub t. So the i's can have a subscript, right? The subscript is sort of implying discreteness. That's just a reminder to you that the state space is discrete. And maybe it was a bad idea to use s over here. That s is meant to be a little s. That's not the state space. I hope that's clear. Okay, so anyway, back to business here. The Markov process is called homogeneous if this probability can be rewritten. So x of s is equal to I sub s. If this thing is the same as, so let's give ourselves a little bit of room. I think I can fit this in maybe already, but just in case. If this thing is the same as the probability that x of t minus s is equal to I sub t, given that x0 is equal to I sub s. Right, so what are we saying by this? We're saying that the t and s don't really matter. T and s don't matter, but t minus s matters. Right, so that's my sort of paraphrasing of that definition. I should probably put that maybe off to the side. That's not part of the definition. All right, so let's think of some examples here. Essentially what we're trying to look at are things that are continuous functions of time, but that describe discrete state spaces. And so some examples. And they're kind of fun to think of, I think. You can sort of ponder these over your extra week between this lecture and the next ones. And so here they are. So x of t could be like the status of a disease in a population or in an animal. Status meaning they have it or they don't. Or number of people that have it, or number of animals that have it. Disease in a population at time t. Right, so the discrete, so status of disease means like they have it or they don't, or the number of people that have it, or the number of the population that have it is discrete. But so the COVID cases are a good example of this. The number of people infected with COVID today, that's a discrete number. There's no half people infected with COVID. But the time that you're interested in is continuous, at least in principle. Maybe you only work in days, and you can sort of force it to be discrete. But in principle, it's continuous. Another example, x of t, could be the number of objects in a queue. The number of people, say, waiting on hold to talk to their their high-speed internet company. That's infinite. So that's a discrete number, but you might be interested in it happening at any given time. So of course, you can see here there's lots of different examples you can come up with, and then we can try to imagine some applications as we go forward. X of t might be just some general population. So the population of Scotland, say. Or x of t could be, I mean, we could just keep on going, right? Just trying to think of things that are discrete, that vary with as a continuous function of time. Number of shares owned. In some company at some time t. That's a continuous function of time, and so on. So there's just basically we're just looking for anything that has a discrete state space and is a continuous function of time. Okay, so that's all for today. We finished off our discussion of branching processes, or more specifically, Galton-Watson processes. Those are the only ones we looked at. And we just and we did that with a fun but weird, contrived little example where you look at a population that has to have 3 children, and you try to figure out whether or not they carry along some trait. That was kind of fun. We just barely defined a couple of things related to Markov processes, which we'll spend a lot more time on as we go forward.